we're having some problems. It kind of disconnects from the stream is the one. So sometimes we disconnect, just reconnect again, and we will restart. But the stream works still. So how do you know that? You will be on that. You will see again when it says connect. So I will just that doesn't mean that the stream was out of password. It means that it's simply there's no communication between this and the camera. The camera is still streaming to YouTube. So don't worry about that. So if you want to ask me don't have this ring red, it means that it is streaming. There's some problems with
So did you get this all working? Did we figure out the streaming, live streaming part? Did you see that message that came from one of the students?
Yeah, the thing is that there was a button that should have this.
Okay.
Basically ensures that we are closing the streaming, and then there's another button that's done.
And you've done it this time?
So the last time when I closed it, I just directly pressed the down button.
Yeah.
Before that, I should have pressed that. I didn't close anything.
Okay.
I missed that.
Okay. So this time you got it. Perfect.
Okay, I think we should begin. Welcome, everybody. Welcome back, those who came back. It's not as full today. That always happens. Just a couple of questions. So, there are 3 sections here, and I just checked, and there is 1 open seat in 5955, and there's 4 open seats in 6955. So who here is like first on the list for either one of those sections? Number 1 on which one?
Sorry, it's like the what was the 2 number? I think it was the.
Either one of the. If you're first on either one of the CS ones.
Yeah, I'm on one of those. Yes, I can tell you maybe why it's
So-
not popping you in.
What's that?
I might be able to tell you why it's not popping people in.
Yeah, tell
I
me.
think there are. Is that I guess it's done in a batch process, so it's done like a couple times a day. So if somebody dropped recently, like if someone dropped to 12, then it doesn't run again until 7 or something.
I don't really understand how that. Yeah. Okay. If that's how it works, that's weird. I don't know. I don't know why this is the way it is. There are tons of people on the waiting list.
Yeah.
So why they're not going through, I don't know. This is like a computer problem. Not really. So I don't understand. If you're on that list, if you're in 6955 and you're 1, 2, 3, or 4, like as far as I understand, you should be having your opportunity if you qualify, I guess, for like the class. Like I don't know if it takes into account. I don't know if it takes into account like your status as a student, and if it allows you to get into the waiting list without qualifying for it. And if that's the case, and then somehow is blocking it, that's also like totally weird. I don't understand how that works.
Right. Like scheduling conflicts or something like that.
Not really sure. So after this class, we'll check again those numbers. If you're 1 through 4 in 6955, or you're 1 on 5955, come talk to me and show me that that's the case, and then we'll figure something out. We won't wait for the waiting list to get reprogrammed in the right way. Okay. by raise of hands, who is in 5955? Right. Who's in 6955? And who's in math 50 or 7960? Kind of all set. Like kind of in columns. Nicely done. Great. Well, hopefully everybody who wants to propose with 5 seats available, that should work out. Okay, so we're going to go right into it. We have our kind of fun intro. Now we're going to start to slowly get into what it is we're going to be doing this semester. And today we're going to start by talking about like one of the core tasks that we use neural networks for, or where they were like first shown to be very useful in this idea of image classification. Oh, this one. Okay. So it seems like we should have like where are the slides? I don't know. Are there ones for the side? There we go. How about? Okay. So, image classification. So, this can be posed in a number of ways, but the basic idea is like we're going to have a data set like this. It's going to have things in it that we recognize, and we want the computer to be able to look at that and say, hey, there's a cat in this image. It could be more complicated than that. It could be that there's like a cat and a dog and a car and whatever. We want it to tell us all the things. It could be that we want to just, instead of knowing that there's a cat somewhere in the picture, that we want to know all the pixels that are part of the cat, as opposed and different from the pixels that are not, and so on and so forth. But we're just going to we're just going to start off really simple. It's the simple problem of like there's one object in each image, and there's 10 of those possible objects, or maybe 1,000, and we just want to be able to pick the right one. So what makes this tricky is that we see this, as a rendered image, but what the data that goes to the computer is basically just these, multi-dimensional arrays of numbers. And so, how is it that a computer learns to like associate a cat with like all these arrays of numbers? So that's what we're going to try to build up today. When we're doing images, we typically have arrays, usually of this, some height and width, and then usually 3 channels corresponding to 3 color channels, and then we get from that all of our rendered colors. And then often that, what's the number that's in the array is some number, expressing the intensity of that color at that pixel, or that color, the primary color, red, green, over there. Okay, so great. So we have just a bunch of numbers. Somehow we're going to figure out there's a cat in there. There's a lot of challenges to this. So we're looking at this cat from, I don't know, almost like in front of it, but like we could have another picture where it's on the side, or up above, or down below, or whatever. Each one of those has to correspond to a cat, right? So it's not just like we don't want a good system won't just recognize a cat from the front, it'll recognize a cat from all sides. What other kind of problems are there? Well, so another one is like illumination, right? Like we might have, it might be very dark in the picture, not very light at all. It's hard to tell the features, distinguish the colors, textures, things like that. It might be that like only half of the image is illuminated. It might get really bright, kind of saturate the image. There might be a lot of other things going on, like just like in that last picture, like there's just an outline of a cat. And still, we'd like this to be, able to tell in all these cases that there is a cat in the image. Cats also are very flexible, so they take on all kinds of strange poses, as you might be able to see here. You really like cats a lot. Are these adorable to you? You're like, oh, cute. It's like the worst looking picture of a cat. Even my hair. Okay, so we have to recognize all these are cats, even when they're like the bodies are already weird. Here's another really hard, very hard problem. We might only see a part of the cat, like in this case, just the face under this blanket, or occluded by all this grass, or even worse, just seeing a tail there. So there's a lot of challenges here. Just thinking about what this problem is like. There's a lot of challenges here. There's no background color, right? So like the cat might kind of blend in with the background, and being able to tell the difference between the cat and the background could be tricky. And cats come in all kinds of colors and shapes and whatever. Okay, so what are we trying to do? We're trying to basically create a function where you put the image in and it spits out the right label. So in this case, in all these cases, we want to spit out the label cat. So you might, if you didn't know anything about machine learning or successive deep learning, you might just like start and say, okay, I'm just going to write a program for doing that. And you'll start to kind of think about all the heuristics, take all these examples, and you'll say, okay, well, it's got to have, I don't know, like cats have these kind of pointed ears. You might try to figure out pointed, like something that detects pointed ear in a certain shape of a nose or whatever it might be. But you'd fail at that miserably. Like this would be a miserable task. The more you try to figure it, try to do it, like the worse it would probably get, because you just keep coming up with more and more exceptions and realize that it's a completely futile exercise. So there's really no good straightforward way of doing this. So enter machine learning. So I forgot about this. Yeah. So attempts have been made to kind of extract features that would maybe allow you to do this, like get at pointed ears and things like that. Like kind of produce histograms of all the corners or other types of edges in a picture, and somehow detected the cat that way. But these also failed miserably. So the machine learning way of doing this is to say, let's just see all kinds of examples of cats and all the other classes that we care about. Let's just have all kinds of examples of them and have a method by which we have our function that gives us the label is some very flexible kind of parameterization of a high-dimensional function, and have some method for refining what that function is so that it accurately associates with each of these pictures the correct class. And this is like this is like the essence of machine learning. Is we aren't going to hard code our functions that take us from image to class. We are going to learn those functions directly from data, from labeled data. I think I called this out a little bit later, but we're going to see this data set over and over and over again. There's actually 10 classes, and there's only 5 of them for some reason. But this is called CFAR 10, and it's very basic, but it's like a kind of a core basic image data set for illustrating machine learning ideas. It used to be kind of a state of the art, but then it was quickly replaced by things like ImageNet. Now there's so many other ones, but it was kind of small and only 10 classes. But we're gonna see this. So like basic, yeah. So we want to have a method for learning the function, and then once we learn the function, a method for giving us the correct label for that function. So training and inference of prediction. So before we get into like all the really sophisticated methods for this, let's think of let's go through an example of something that's far easier to kind of intuit. It still uses data, and this is the idea of using nearest neighbors to classify images. So the idea here is that you're given a training set like those images, and basically the training is you just store all those images. You represent them in some way. Like this would be, you take all those images, maybe make one long vector out of all the pixels, and then you would just do some sort of vector-vector comparison. And the thing that's closest in that similarity comparison measurement you would say, okay, well, since it's closest to this, I'm going to give it that label. Or you might say, if it's closest, like the three things it's closest to, like the dominant label there, we'll call it that. So this is a thing. You've probably seen this before. Nearest neighbors, k nearest neighbors algorithm. This works actually really great for certain types of data, like tabular data sets. But it turns out it's not great for image sets. We'll talk about that for just a second here. Okay, so here's all the 10 examples in CFAR 10, or our classes. Airplanes, automobiles, bird, cat, deer, dog, frog, horse, ship, truck. I have no idea why it's these 10, but that's what it is. And what they're showing here is, like, if you do this nearest neighbor classification, here's what you would get. So you memorize all these things, and then you'd give it an image it hadn't seen before. And the resolution's not awesome, but like, here's like an easy one to kind of see. There's this frog here, and what's the thing that's closest to it by doing this kind of vector similarity, just comparing all the numbers and picking some way of measuring the nearness, and then saying, okay, here's the nearest one. Well, turns out this is a picture of a cat, even though the resolution's bad there. The next nearest one's a frog, and it's a cat and a frog, and then an airplane, and another cat, it's like a stamp, and a frog, and a car, and an airplane, and a boat. And you can see why it picked those. It really has nothing to do with the fact that those things look like frogs. It has everything to do with the fact that there's like a white background, and there's something kind of shaped in this kind of diagonal way, kind of sharing the similar colors, right? And if you look at all the rest of the examples, they're like that. What's another one? Yeah, like this dog one right here. So this isn't great. Why isn't it great? Say something. Somebody raise their hand and say why this isn't great. I got it wrong. That's like a consequence of this not being great. But why isn't it great? Why is comparing pixel values not great?
In the sense of this, the percent success is really low.
Yeah, so like that's a result of why this is not great. So what's happening here that's not great?
It could be that you're just looking for darker images because your training set had a bunch of darker images. So you just end up looking for darker images and that.
Yeah, right. It's in the back there.
This example is just using one training image for each class, as opposed to like trying to figure out the similarities between.
Well, that's not necessarily true. But basically, all 50,000 images are being used as a training set. But it's like it hasn't done anything to train. Like it's done no training. It's just like memorize them, and it's just looking up. Every time you present it with the test image, it's just going through all 50,000, seeing which ones are the closest to it, and then just presenting them from like closest to furthest away. Yeah.
So looking at the pixels in the same position, not necessarily.
Yeah. This is the problem, right? It's comparing. When you do this, if you think about this, like you're comparing numbers in the same like entries in these arrays. So it's comparing like pixel per pixel, and that's why you're getting this with the white backgrounds, because like all of these pixels here are really close to these pixels here because they're both white. And then when you go over here, all these pixels are really close to these because they're kind of the same color and in the same shape. That's totally not what we want here, right? We don't want this to do like pixel per pixel comparisons. We want it to recognize that there's a cat there by some other means that has nothing to do with like the exact location of the pixels. Whether the frog shows up in the middle or up in the corner here or this corner here or turned upside down or whatever, we still want it to recognize that there's a frog there. So like these kind of like rigid translations and rotations, like whatever learning algorithm we have, we want it to be independent of that. Good. There's lots of ways you can do this comparison. There's an L1. This is kind of like a math reminder, but it's basically this is showing you like pixel per pixel comparison, right? It's like this is very simplified, but in this 4x4 grid that represented our image. Here are the numbers here. Here are the numbers here. What's one way to do these comparisons? You just do the entry-wise Subtraction here, just 56 minus 10 is 46, 32 minus 20 is 12, and so forth. And then you take the absolute values of those. That's what these things are out here of each one of those entry lines, and you just add them all up, and that gives you some sort of notion of distance that depends on the pixel by pixel matching. There's other measures here you could use. Doesn't really matter. They're all going to be bad if you're doing your nearest neighbors for images. So again, like how this might look in code, in Python, there's this train step, and all this train step is just like take the training data and just keep it in memory. Take the labels, keep it in memory, and then use that for lookup. And then when you do lookup, you just kind of go all, you just loop over all the test sorry, this is looping over all the test examples. This is doing a comparison across all the training examples, and then just arranging this by the smallest distances. Okay, there's another reason why this is actually bad, not just that it's doing pixel per pixel comparison, but there's kind of like an algorithmic complexity argument here. So with n examples, how fast is training here and how fast is prediction? This is like a big O of something here. So with n examples, how fast is training? Big O of
Constant.
Constant, exactly. And how about prediction? Big O of n, because you got to loop through all the training examples. That's bad. We want the inference step to be fast. We don't want it to depend on the size of the data. For the training, I mean, if we can get like a perfect classifier, we're okay to wait around a little while, right? Because then once we have it, we can just keep using it. It's fast. So we're okay. I mean, we want the training to be fast too. So don't get me wrong. It really sucks to wait around for a couple, a day or weeks or something. Some of the stories of some of the early training that took like months to do. That's not fun. But when it's all done and it works, you're okay because other methods would be fast on the inference step, the prediction step. So this is also why this is bad. And then kind of getting some idea of what this looks like. You get these really, really kind of funky boundaries for deciding. So what this is showing you, this is not CFAR. This is like in a simple 2D data set. But you get something like the following, where what you're seeing here is all the training data, and then the boundaries here between the classes. And this is the case for k equals 1. So you're just looking for the nearest training point, and then you call that. You give that the same label as the nearest training point. So all of the space here in purple, it's nearest to a purple point. All the space here in green is nearest to a green point, and so forth. And this is particularly bad because these boundaries are really goofy, right? They just depending on the sample of data, training data you got, you're getting these really rugged kind of goofy boundaries between the classes, where it's far more likely, and this is like stuff that we impose on our models, but it's far more likely usually for there to be some more, far more smooth boundary between the classes, right? This ruggedness is a consequence of having sampled a small number or a small, a sample of data from the actual population of things that we care about. And these islands are the same thing, right? Perhaps this is just poorly labeled data. It's sitting in the island of green. That may or may not be the case, but that's also something that we probably wouldn't expect, given that we had a good representation of our data, which pure pixel values is not, but still. And what's happening here is that you have, if you use your three nearest neighbors and take a majority vote, or your 5 nearest neighbors take a majority vote, then you start to get, less rough boundaries, but still, and actually it's out in the island in this case, but still it's not, this is not great. So we would call these models really irregular. And one of the techniques that we'll talk about in this class is like how to regularize models so that you get like smoother boundaries between your classes.
Is the white just indeterminate? Like the white on like K through K?
Yeah, it is, right? So I guess, what my guess is that for all the points in here, these 3 points are closest. So there's no majority. Yeah. And so forth for the other examples. Okay, so again, another reason why these might not be so awesome. Okay, so what does this look like? We already kind of went through this in the previous picture, but you know, for the majority of these things, the nearest neighbor to this test is not of the right class, so we don't really like it. It's just looking for things that are closest pixel boundaries. Yeah, you can pick different distances here. You actually will do some of this in your homework, just kind of warm up for doing some classification stuff. Use these different distances and see what you produce. But you know, the idea here is just kind of showing you like depending on, this is like another thing that makes this a little bit hard, although these kind of decisions happen in most everything we do, whether it's neural networks or nearest neighbors or some other classification, is when you pick a distance, you're basically picking a geometry in which to like do the comparisons, right? So this L1 distance, what this is showing you like the sphere, like the unit circle in 2 dimensions. So it actually looks like this diamond in L2, which is a typical Euclidean distance. You're getting your nice, smooth circle. All mathematicians are like, yeah, totally. I already got this like a long time ago. But if you haven't seen this before, like you're choosing a geometry in which to compare these things. So like what's closest depends on obviously how you measure. And there's lots and lots of measurements you could use. And you get, not surprisingly, slightly different, you get different boundaries depending on how you pick these, your similar measurements. Okay. There's another issue here, although this is definitely a part of like training neural networks, is that you have these notions of hyperparameters, right? So in nearest neighbors, there's basically one hyperparameter, and that is how many nearest neighbors to use to do the vote. K. So in K nearest neighbors, K refers to how many of the nearest neighbors to use in choosing the label. So like, how do you choose that? We're going to see this a lot with neural networks. This is like, if you think one hyperparameter is bad, wait till there's, lots more than that, and you wonder what to do with those. But still, there's this idea like, okay, I pick one. So like, if I pick one, K equals 1. How is that compared to K equals 5 or K equals 10? How do I know which one's best? And the answer here, which is really unsatisfying, is that really it's just problem dependent. Like, it depends on the data set you're using. It depends, This is true again for K nearest neighbors as it is for most machine learning algorithms. And really, what we have to do is we have to go through some process of deciding which hyperparameter we're interested in. And there's a whole host of tools and ideas around how do you pick the best hyperparameters, and how do you do it in a way that doesn't suffer from things like multiple hypothesis testing and things like that. But here's like the basic way. And again, this is like a review of like basics of machine learning. But it's good to kind of run through this one time all together, just so this is going to be part of it. So this is how we typically think about how to set hyperparameters. So we have our whole data set. And let's see. Yeah. So this is our whole data set. But this is I should say on here your training set. So just think of this as just your training set. We've held out the test set, because we don't want to train on that. We want to test how good we are on the test set. So we're just thinking about the training set right now. And then, okay, so how do you use the training set to choose your parameter, in this case, the k for k nearest neighbors? In red there, it says k equals 1 is a bad choice because it always works perfectly on your training data, right? So it's always going to pick itself on the training data, so it'll always get it right. So it's some, you have to be clever in picking this. Like you have to do something different than just like working with the whole data set. So what you typically do is something called cross-validation. Here's the idea. So this will say test, but this is like a validation set from within your training data. So what you want to do is you want to split this up, and then you want to run through your hyperparameters here and test them there. And what you want to do, because you still have one more holdout set, you want to oh, I have it set this way. Good job. Okay, so it has a test set. There's a validation set. So never mind. Now we're down here to the third one. So you pick this validation set. That's how you pick your k, and you test in the test set, just like I said before. But now I have an actual row here. I forgot I had that. And what you want to do here for cross-validation is to do this many times. So you have your whole training set. You hold out your test set. You never look at that till the very end. There's two kinds of overfitting that we're basically trying to prevent against here. One is overfitting to the training set. The other is overfitting of the second kind, which is overfitting your hyperparameters. So the way you protect against that is cross-validation. So there's usually, you might pick 3 folds, 5 folds, 10 folds. It doesn't really matter. You pick some number of divisions you're going to divide your training data into, and then you you hold out one of those folds and you train on the rest. Again, you're trying to figure out which, in this case, which hyperparameter to pick. You validate it here. You do that for all the folds. You get like an average, in this case, like an accuracy in classification across all those different folds, and then you change your hyperparameter and you do it again, and you can get a plot kind of like this. So what this is showing is at each k what our accuracy was on all 5 of the folds. So k equals 1, 2, and so forth. And what you see here is like a definite pattern that's going to show you up here, right? For very low k, we have lower accuracy. For very high k, we have lower accuracy. But as we start to move into kind of medium ranges of k, we're getting like empirically the best accuracy here. And so we pick that, and then we go to the test set and we go compute our accuracy. Otherwise, we're going to overfit ourselves to the test set, and that's a no-no and a mistake that lots of introductory or like kind of new machine learning people will do. Questions about this? Questions about the idea here? Cross validation.
So as you're if you're like working with the data set that's always growing and growing and growing, do you still kind of use this same type of thing? If you know you're
so like that, that's a very different like scenario, right? So like this is all about fixed data sets. If it's always growing, you probably want to have some sort of strategy for deciding which of, as it grows, like that new portion, which of that is going to go into your augmented test set and your augmented training set. And there's lots of like fancy ways of kind of doing like an online type of approach for updating hyperparameters and things like that, which we won't cover in this class, but these things exist. But the basic idea is just you always just want to be splitting whatever new data you have into these training and tests, and then you might retrain everything, or you might just update on those on the new training, like update your parameters in the new training set or something like that. But it's best to think about this in like a fixed data set kind of way. If if you truly have like real online, like you receive like you're wanting to train, like you can't train in batch, you have to train online, and you really need to do something different than what I'm going to show you. Other questions? This is again just basic machine learning.
On your final training, would you include the test set or no? That's never trained on ever.
Well, it just depends on like what it is you're trying to do, right? So the whole point of like having a test set at all is to see how well your model generalizes, you know, to held out data. That should be like if you sampled it correctly from your whole data set, it should be, you know, roughly of the same like distribution. And so you're just trying to you're estimating the generalization there. This is like the most formal way of saying this. And so if you do all that and then you go and you just train on everything, there are no guarantees that this thing is generalizing well. But you know, if it did generalize well to the test, then and you feel like you need to have that extra data for some reason, then you can go ahead and do it, right, and just use it for inference. But you wouldn't, you know, like you kind of broken the contract you made with yourself. Like, you know, this, like the thing I estimated was done in, you know, like a statistically sound way. You kind of broke that, but it's done a lot actually. To, you know, after you've picked a whole architecture and the parameters for it, you know, by doing this split in the training and test, and then do the cross-fold within the training, you know, that's basically allowed you to do this whole like hyperparameterization, not just of like a K and K-mean, but like all like the whole neural network architecture. Then oftentimes you might just add that back in and retrain something else. But I don't know. It's a little bit cheeky to do that.
So you're not a fan?
No, I actually am a fan. If you don't have tons of data, like if you need it. But if you have tons of data, you don't need to do it.
When you decide the validation and test rules.
Yeah, like, are you asking like how many folds or like how to do it?
In terms of percentage, how do you decide?
Yeah, so when you're doing classification like this example is, what you often want to do is you want to create, this is true for the test set and all the folds, you want to create what are called stratified splits of the data, which means that you have an equal proportion of labels in each of the folds. So like every fold is representative of the original like distribution of classes. So like, you know, if it's a binary classification problem, like I said, you have, you know, zeros and ones as labels. There's just two classes, and like there's like 30% zeros and 70% ones. And when you subsample this, you actually want to sample it with respect to, like, you want to preserve that balance, so that in every single fold there's 30% zeros and 70% ones. Actually, the binary classification, if you're unbalanced like that, you should be doing some other things, because that can throw off how good your classifier is. Like it.
So for the validation and test,
Yeah.
How much? What's the thumb for deciding if the class labels are unevenly distributed?
So just they're going to, so in the whole data set, they're going to represent some fraction. You know, each class will represent some fraction of all your examples, right? And you just want to preserve that when you go. So you typically, you know, so like a typical way to do this is like, okay, so I take all my data, I'll split off like 20% of that for test. Okay, that's like a typical, you know, 80 training, 20. There's really no good rule there, but that's kind of something you do. And then you go on this 80%, and you divide that up like into five splits, evenly sized. And then within each, when you do that, you want to do it randomly, but with respect to the class frequency, like that histogram, to preserve that in each one. So that it's, again, what you're trying to do is you're trying to like have representative subsamples of the whole data set. But there's all kinds of arguments around maybe times when you wouldn't want to do that too. Like, don't take these as like, this is like, you have to do this every single time. It would be good to do this most times. And as you get more sophisticated with this, then there'll be time when you think, like, maybe I don't want to do it this way. Like, for instance, when you have like a binary classification problem and your classes are really imbalanced, you oftentimes want to like oversample the class that has very few examples in it, because what's happening in your algorithm's not seeing enough of these low frequency examples to like learn from them. So it actually, and if you're not measuring like how well things are going with respect to that balance, you can really get yourself into a situation where you have a very poor classifier, but it looks like it's really awesome because it's just learned to classify with respect to like the majority, like the majority class. Yeah.
When you have a situation like that, does it ever make sense to like weight that imbalance? So
Yeah. So there's techniques. Yeah.
That more.
Yep. So there's techniques for that. So like usually weighting, what it means is that you're oversampling according to that weight the lower frequency classes. Like you just basically like you're just sampling the classes with like in a way that's like 1 over the frequency, so that you in the end you're sampling them all kind of evenly. Like the sample data will have each of the classes will be evenly represented like number of samples. It's just that what will happen like in the low frequency classes, you'll see the same examples over and over again. Yeah. I don't really need to get into that, but it's definitely a part of machine learning. Other questions about that? Yeah.
Well, they graph the sample lines. The different holes used.
These lines, these are just like mean. Like there's in the middle of it's a mean, and those are standard deviations. So
different folds.
Yeah, of the different folds. So there's 5. So at each k, there's 5 dots. So yeah, it's just a way of kind of seeing the summary there.
So we can see on the graph that for each fold, the cross-validation accuracy is still increasing, right?
Mm-hmm.
So the lowest will be the fold 1, and the highest will be fold 5 or something.
Yeah, 7, something like that. That's a 7.
So you can say that the network or model is still learning in the cross-validation.
Oh well, yeah. I mean, there's not really learning here. This is not the same as like this is a loss function and like these are the epochs that, or iterations of training or batches or something like that. It's not that at all. This is cross-validation of hyperparameters. So this is like when it's all trained, even though here's k nearest neighbor, so there's no training. But like after it's all trained, then you evaluate it.
But then how the cross-validation accuracy is increasing with each different code? It should be same or
no. So it's not. I think you're misunderstanding. So like here's k equals 5, and there were 5 folds. So this was my accuracy on like they call this was like fold, like I trained on folds 1 through 4, and this was my accuracy on fold 5. And then this one was like I trained on 1, 2, 3, 5, and this was my accuracy on fold 4, and so forth. So I have one of those for each of these, and I'm drawing a line through the means of all those. So it's the final accuracy on the fold, and I haven't even used the test set here, right? I've just been doing this inside the training set. Does that make sense? Okay.
So why for the k equal to 100 and for each cross folder is C, right?
Yeah. So why does this go up and then come back down? Is that what you're asking?
No. I mean for the k equals to 100 and for
why are there only 3 dots?
Yeah, right.
Well, they're probably like laying over the top of each other. Okay, cool. All right. Yes, k nearest neighbors. I already said this, I think, a few times. K nearest neighbors on images is never used. So we already said that it's slow at inference time, prediction time, and then distance metrics is pixel by pixel are just totally uninformative, and they're missing out all kinds of weird examples, right? So these two should show up really close to each other, right? But they may not if you have these kind of weird occluded regions, or if it's shifted over a couple of pixels to the right or up or something like that, or if the illumination's changed, or you had some sort of color change to it. These even though the pixel by pixel you'd have something similar there, because you changed the color, you know, all the RGB values changed, and so now these things are like really far away in color space, right? So is anybody not convinced that your neighbors is bad for images? That was like my one job, I think, just for the last hour. And if not, here's one more argument. Who knows about the curse of dimensionality? This is like a phenomenon that comes up over and over and over again in doing like statistics. But it's basically that like the more dimensions you have, the more things are just naturally separated from each other. And you know, in certain kind of contrived situations, you can basically show that like everything's like uniformly distant away from everything else as dimension increases. Even like for a random sample, even though these things follow some well-behaved distribution. So, anyways, don't do it. Don't do it. Let's do something else. Okay, linear classification. So, why linear classification? Because neural networks are built up layer by layer, and each layer is a linear model, a linear score function, followed by a nonlinear, what we call activation. So like something you apply to the some nonlinear function you apply to the outputs of the linear score function. So we're going to go through what linear classifiers are. You're going to do some of this in your homework. We're not like, what we're not doing here is saying linear classifiers are the way to go for particular problems. What we are saying is that let's understand what these are so that we understand what's happening at each layer in a neural network. And there's just a picture of block Legos showing the layers. All right, so back to CFAR. We're going to be using this again to illustrate some of the ideas around linear classification. Yeah. Okay. A slightly more general way of thinking about this is to say, okay, we have an image X. We're gonna give it to a function f that's got some parameters w, and then it's gonna give us a score for each of in CFAR 10 for each of the 10 classes that are in that data set, and we're going to use those scores somehow to make decisions about what's in the image. Okay, so like this is this is general in the sense that like f is just some function that's parameterized by some weights w and takes as input our image, this array. In the case of CFAR 10, 32 by 32, so these square images. They're RGB images, so there's 3 channels. Anybody freaked out by the fact that like maybe your whole life you've been like doing math with just like matrices, and now all of a sudden there's like another dimension here? Feels kind of weird, huh? This is a big jump. It's not really clear why we don't teach higher than matrices in like linear algebra courses, because these days it would be way more. It'd be very useful to just always be talking about tensors from the beginning. But this is like the reason why, like TensorFlow is called TensorFlow, because it's like flowing tensors. It creates a graph, a computation graph for moving tensors, usually your input image, through all these transformations that give you, tensor in, tensor out, and they keep changing dimensions, but it's very often very high dimension, or like the number of directions or ways in your tensor is often larger than 2, so it's not matrices. So if like this is like, I'm just pointing it out that like that's not, I don't expect that to be a kind of a given just yet. That we also have like higher dimensional arrays. But fortunately, all the software we're going to use just treats that like it's no big deal, because it isn't. It's just one more index. Okay. For a linear classifier, our function is going to be, guess what? A linear function. So the parametric form for our f when we're doing linear classification is to take the weights and to do a matrix multiplication with the or to do a tensor multiplication, or whatever is the size of our input here, or to do that multiplication with our input. So it's a linear operation on our input. But again, what is the output? It just gives us 10 numbers that we think of as scores for each of the classes. We're deciding, to help us make a decision, what is in this image. So one way to do this is to take this input here and turn it into one big vector. So 32 times 32 times 3, which is apparently 3072. You can check me on that. And then to pick our parameter, to pick our weights, our parameters is this weight matrix. Sorry, these weights to be a matrix arranged as a matrix of 10 rows and 3072 columns. So that when we do the multiplication, the matrix multiplication there, we get a 10 by 1 output to a vector of 10 numbers, right? That's what we want. We wanted to get scores for each of the classes. Again, this is just like one way to do this. You could think of lots of ways to do this from like these higher order tensors, but this is a very straightforward way to do this. Also, we will do this a lot. We will often add a constant vector of the same size, in this case 10, length 10, called the bias. And it's just like, it just gives you a few more parameters to learn. So, and if you think about what's happening here, so this is still a linear operation, this wx plus b. What's happening is w is doing some linear transformation from this high dimensional space of 3072 to this low dimensional space 10, and then the bias is giving you some sort of learned offset from 0. So like, if I input 0 as x and I multiply it by w, no matter what w is, I get back 0, right? So this is mapping 0 to 0. But that may not be the most advantageous transformation that I can make. So to make it slightly more complicated, but not that much more, we allow it to learn what's called a bias, which would just take 0, it gets mapped to b. So it moves it away. And that allows you to kind of just, if you think about us in terms of classification boundaries, it allows us to move that boundary around in some advantageous way and not have all the boundaries pass through 0. We'll see some pictures here. That doesn't make sense. We'll see some pictures here in a second. But this is the most basic linear function we could use for producing these 10 scores. Okay, so how does this work? Like I said, again, in this really simplified form, you take your image, you stretch it out in one long vector, you start with some weights w, start with some bias vector b, and then you do all the multiplications, and you get out these crazy numbers. In this case, negative 96.8, 437.9, 61.95. And these are, again, there's 10 classes, but this is just simplified again. So like, here's our cat score, here's our dog score, here's our ship score. It doesn't feel like much yet, right? It kind of just feels like the most basic math class you've ever been in. But what's happening here is, I'm going to go to this next picture. Okay, so this is the most basic math class ever, in the sense that we're just doing these linear, like algebraic operations and getting out these scores. And what's interesting is, so we're going to talk about this next week, like so I said we start with some parameters w and we start with some bias b. Next week we're going to talk about how do we set this problem up so that we can change those parameters w and b so that we can do our best on classifying these images. And that would mean we have to do one more thing too, which is to turn those scores into something meaningful for deciding for making this decision. But for right now, just think of it as like the largest score amongst all the 10 that we would get out is going to be, you know, what we call how we classify that image. So when you do that, what happens? Well, what happens, what we mean by that is like, what W will this thing learn? And this is the thing that is learned here. So in some optimal way of optimizing our W, remember W is 10 by 3072. So when we sort of optimize this and got like the best W that like helps us get the highest score most often for the right class, we can take each one of those rows. We know that the first one like corresponds to the first class plane, and the second one should correspond to the second class automobile, car, and so forth. And we can put those back into a 32 by 32 by 3 tensor, and we can visualize it. And what we see is what is a linear classifier doing? It is basically learning a template, like a prototypical template of what each of these classes ought to look like. It's like trying to match sort of pixel for pixel. Trying to do that the best across all of the examples in our training set. So it's a lot like the k nearest neighbors in the sense that like it's still doing some like pixel for pixel matching. However, it's doing this in a way that no longer is like specific to each training example, but it's sort of like bringing all the training examples together into one kind of prototypical template. So here's what they look like, and you'll actually get to produce these in the homework as well. It's kind of fun to do. Here's what they look like. So this is the row that's getting compared to the image for plane. So like if this thing kind of looks like plane, when you do this row column multiplication, if it kind of looks like plane, so if it is a plane, like we expect it to kind of look like this. Or if it is a car, we expect it to kind of look like this, or bird or cat or so forth. When I look at these, like, I don't really see a whole lot of anything, right, other than like really mushy shapes. Maybe the easiest one to kind of like pick an object out of is this horse, and it ends up being like this two-headed horse, right? Because some of the images in CFAR have a horse pointed that direction, and some of them have a horse pointed this direction. So it's learned that, like, you know, I better have a template like this because, you know, sometimes they're to the right, sometimes to the left. And you can see that like the colors kind of, like the background colors kind of correspond to where you'd expect these things to be, right? So like a plane ought to be like somewhere in the air, right? So it kind of has this like surround of blue. And, you know, I don't know, birds or deer birds should be up in trees, so they're kind of surrounded by green. It's like, it's like mashed all of the training examples for these classes together and giving you one sort of prototypical example. And because you only get one, it's really kind of a mush of a model. It's really not recognizable. Nevertheless, this actually doesn't do too bad. It actually works pretty well, and you'll get to explore that in the homework. Okay. Yeah, questions?
There's such a diagram on the right. Why B is just y is just 1 number, x is just 1 number? Shouldn't be a matrix?
Yeah, well, so again, like this is like the simplified example, right? So if our input ends up being very simple, like 2 by 2, then your weights are 2 by 2. Or sorry, you know this. No, that's actually wrong. So it should be 4 by 4. So we'll go back to this picture right here. So they start off 2 by 2. These should be when you stretch them out, it's going to be a vector of length 4, and so the row should be of length 4 as well. So like that kind of caricature doesn't preserve that very well. So it's okay to be confused by that. But yeah, it's just, I don't know, it's just trying to character, just a caricature of it. So like these, yeah, think of these as being this is still, yeah, it's still, these are still the 4 numbers that would show up in the row for, like, say, plane, right? They just haven't been straightened out like in that one picture that we showed you. So they still would match up with, like, you can still do the multiplication, the entry by entry multiplication with the input image. And then you just have the bias. So, like, this is just, this is like the first entry in B, the second entry in B, the third entry in B. This is like the first row in W, the second row in W, the third row in W. Even though it's not looking like rows. Matrices. So it's a little bit confusing, but yeah.
Still position related because the fourth zero it's left of if for force its orientation is downward, it's maybe not classified very well.
You're saying, like, if I got a picture of if one of my worst pictures was actually like lower here, yeah, so it's not going to classify that very well, right? That's the limitation of the linear classifier, is that it's learning like this one row. It's learning this one row of numbers that represents the horse. And so what the position it does take is something like the mean position of all the horses in the training set. And the reason why there are 2 heads is because, and actually it sort of seems like there's more of a head to the right than the left, which maybe indicates, I don't know the answer, I've never gone through the examples like that, but maybe more of the horses are pointed to the right than to the left.
So for the weights, I understand that we're with the weights that we're getting the values from the training data.
Yeah.
But what about the bias? Is the bias?
Well, so again, the weights and the bias, they're learned from the training data. They aren't in the training data. You learn them, and we haven't said anything about how you learn them. We're going to do that when we talk about loss functions and backpropagation next week. But for right now, just believe me that there's some way of, like, using the data to learn the weights in the matrix and in the bias vector. Okay? Did that answer your question? Do you feel get it?
Yeah.
Okay. Cool.
So does those scores also like involve into those final results?
Yeah. So, like, the way to think of these right now, we'll treat this in a much better way when we talk about specific loss functions. But just for right now, think of this as like having been optimized by producing, so the largest number that you get out of this across all the classes is the class that corresponds to is the class that you classify the image with. So the largest number is, you could actually choose this to be different. You could choose it to be like the smallest number. It doesn't really matter as long as like when you do the optimization with this loss function, like that's all taken account of. And when we talk about this next week, it'll make a lot more sense. Does that answer your question? Okay. Yeah, just for right now, think of it as like you just get a list of numbers, 10 numbers. Whichever number is highest, the class that corresponds to, you say that image is of that class or contains that object. Yeah.
Does this become problematic if you're trying to, like, classify thousands or like tens of thousands of things, basically just scaling up all of those? Like right now we only have 10 classifiers. So matrices are.
Well, we have one classifier, but it's producing 10 scores. Yeah, 10 scores.
10 different classes. So this is going to be problematic. If you go to like 10,000.
Well, the way it becomes problematic is that you're going to get a lot more. There's going to be a lot more numbers that are closer to each other. And yeah, so like the problem obviously becomes harder when you have to pick this object from instead of from 10 different things. From 1,000 or 10,000 or 1,000,000. Yeah, the problem becomes way harder because you just have so many scores that are roughly near each other. So, but neural networks do really well on these kinds of problems where like all the other machine learning algorithms, that aren't neural networks don't. Well, I shouldn't say all of them, but like all the standard ones don't. Yeah.
Here we have one classifier, right? So we should have only one weight matrix instead of 3.
Yeah. So remember, and this is like, I won't use this again. I can tell that. This is the first row of the weight matrix. This is the second row of the weight matrix. This is the third row, even though it's been reformatted as a matrix. Bad. Okay. So the point is just to get some feeling of, if you have a linear classifier and you're optimizing it so that it gives you the largest score for the right class, then this is what you should expect for each row, which has been reformatted into an RGB image in that weight matrix. The point is that it still kind of has a feel like the neural, the nearest neighbor, because it's still doing with that, so this is row 1, and then you take the image. There's a dot product being done there in that matrix vector multiplication. That's still like a pixel by pixel kind of comparison, even though it's not the same. It's not like we're subtracting them and looking at the distance between them. There's still a kind of pixel by pixel a comparison going on here. But it's like, yeah, it's better, but it's better because we can layer these things and apply nonlinearities. We're going to do more of this. But this is just at a basic level, this is what you should expect to see coming out of something like this. Are these like mean templates for each of the classes. Oh yeah, and what does this mean? So for each of these rows in the matrix, you've basically learned a line in your high dimensional space. Obviously, this has been projected at 2 dimensions, so we could visualize it. But the point is, it's like some sort of hyperplane in your high dimensional space, and on one side of it, you think of things as being like more car-like than not, and you're more car-like or not, and it's giving you these like very because these are linear classifiers, these linear boundaries that you can sort of like put together in these. In space, they're not all going through 0 because we have biases. If we didn't have biases, these would all this blue, this red, this green would all go through 0. But because we have biases, this moves it away from 0. And now we sort of divided our space, our pixel space, up into regions where we think, cars are, and deers are, and airplanes are, and so forth. And this template here is giving you that like the slope or the orientation of that boundary in the high dimensional space. Linear classifiers are pretty easy to think about. They're pretty easy to train, but they're linear. So if what you need to do is model nonlinear phenomena, then you're going to have a hard time. And here's just some like easy to kind of think about examples, right? So like we're just in the case where we have 2 classes, just a binary classification. We want to classify the pink points and the blue points. We're going to have a hard time doing that with a linear classifier in a case like this, right? Like pick a line here where you're going to get good separation between the 2 classes. There's just no good line there. Same thing for this this annular example here, right? We have like in these coordinates, this is a really hard thing to do. We have, I can't draw a line through here and get perfect or even really anything kind of like good classification. And same thing for like multiple modes here. Like, if I draw a line anywhere here, I'm just going to really misclassify, some of the modes there. So linear classifiers are exactly what they sound like. They're linear. They create linear decision boundaries, and so we can't do nonlinear things. So like, those of you who study some machine learning, you might look at this example and you're like, oh, I know how to deal with that. Kernel methods. I can change the coordinates of my space so that these things actually do become separable in that like linearly separable in that space. And you might think, oh, I have a couple of galaxies, I can do the same thing. You might be able to do the same thing here, but and that's true actually. This is how, like, before neural networks became like a real possibility, there were kernel methods were probably like some of the most used methods for doing like image classification or classification in general. But you don't hear much about them anymore because neural networks can overcome these issues through through different methods. And those different methods is that they are they end up being nonlinear functions just composed out of very simple linear pieces with nonlinear activations. But yeah, so just go into this knowing that like linear classifiers by themselves are not powerful enough to do the kinds of things that would be really interesting. But when layered in this way, they become very interesting. So yeah, we kind of went through these different points of view here on that. Okay. Yeah. So how can we tell whether we've got a good W or not? Oops, sorry, I didn't mean to go forward. So this is what we're going to talk about next time. How do we tell? So for any set of weights and biases, how can we tell whether or not we're doing well? And then how can we use that notion of how well we're doing to update the parameters in such a way that they become better? So next week when we start talking about loss functions, this is what we're going to do. We're going to spend time talking about some of the standard methods for doing that. And yeah, so we're done for the day. So again, if you know your, let's check the numbers here. If you know that you're 1 through 4 and 6955, or you know your number 1 and 6955, come talk to you that day. Otherwise, keep working on homework 0, and see you next week.